Welcome. This is the 13th session on measure theory, the first session on measurable functions. So finally I started measurable functions. Okay. And in the first three lectures where I gave geometric intuitive ideas underlying measure theory, I said about the possible definition of measurable sets. I motivated that. Measurable functions. Okay. So I'm going to start with that definition and quickly establish its connection with respect to the standard definition which you would find in any textbook. Okay. Just because I motivated the definition, I have to say that here. Okay. But it's always a good thing to have. Okay. So let's get started. So let us quickly recall. X is any set and B is a sigma algebra on that. You see that to talk about measurable functions, I do not require any measure. So I would say B is a measurable space. Okay. So I will start with only first real valued functions. F from xb to R, what's a real valued, is measurable if for every interval, if you want to make it even open, okay, in R, look at F inverse of J. So what is F inverse of J? It is by definition set of X in X such that Fx belongs to J. That's it. This is a subset of X and I want it to be in B. It must be measurable. Okay, that is like continuity in topology, inverse image of any open interval should be measurable set in the measure space. Is that clear? Okay, path, review, understand this. And then proceed. I should learn to write well, right? I'm a little reluctant because I want you to understand rather than get worried about my handwriting. Okay, right, let's go back. So let's first look at examples. The most silly example which usually one always encounters, any constant function. Say fx equal to c for all x in capital X. Okay, then this, now if I take any j, okay, either c is here or c is not there, that's it, right? So if c is there, if c belongs to j, f inverse of j is R of x. If g is not in j, f inverse j is empty. That's it, because no x such that fx belongs to this. Is that clear? So these are measurable, so they are in B. Therefore, any constant function is measurable. Okay. A second example is, suppose I start with the subset E of x. Then let's look at, this is called indicator function, i.e. indicator function. This is the word used in probability theory. Maybe I should use this pen. I will not do double one, okay, but I will use only a single one. This is called indicator function, INDCATOR, indicator function of the set E. This is also known as characteristic function, chi of P function. This is what we usually in analysis we call this. Okay, so what is it by definition? I will use indicator function because when I type in LaTeX, chi almost looks like this. So if I have to write something like chi of en, then it's not very clear what I am writing. Whereas with indicator function, typesetting becomes easier. Okay, these are all on extra material, but anyway, come back. Okay, so IE of x, this is 1 if x belong to x, 0 otherwise. Okay, do you remember a Dirichlet function? Dirichlet function is characteristic function of Q. If you want Q intersection 0, 1 in case of Riemann integral, but otherwise it's a characteristic function of rationals or indicator function of rationals, right? Now I want to know when IE is measurable. Is IE is measurable? Notice that this takes values only 2 values. Therefore, if you give me a j, if 0 or 1 does not belong to that, 0 does not belong to, and 1 also does not belong to that, then f inverse of j, sorry, let me call f, okay, f inverse of j is empty, right? Neither 0 nor 1 belong to that, then there's, if 0 belong to this, okay, but not 1, that is 1 does not belong to j, then f inverse of j is set of all x in x, so that fx must be in j. Okay, the only x which satisfies this is nothing other than E complement, because 0 belong to that, right? Therefore this is measurable. Okay, this must be measurable. If EC is measurable, then so E is also measurable. Do you see that? And hence please understand, if this is measurable, okay, then what should happen? If 0 contains 0 belong to j and 1 does not belong to j, f inverse of j is E complement. It must be measurable. That means E is also measurable. And suppose 1 belongs to j and 0 does not belong to j, then f inverse of j for the same reason will be E. And this must be measurable, right? Therefore, and suppose 0 and 1 belong to j, then f inverse of j is all of x. Okay, these are no conditions. Okay, they do not produce anything. Okay, this is a non thing, this is a non thing. But these two things are very important. What do they say? They say something. Therefore, we conclude i.e. the indicator function or characteristic function is a measurable function if and only if E is measurable. E is in B. Okay, pause, review, proceed. Third example is R with the Lebesgue measure M. See, I don't want to look at measure at all. Do you understand that? To define measurable function, I do not require the measure. What all I require is the concept of measurable space. That means a set and a sigma algebra on that. That's it. Isn't it beautiful? Okay. When you learn Lebesgue measure theory per se, you may miss the point. Abstraction helps in some sense. Okay. Now let us look here to be R to R continuous function. Then let J be an open interval. Then this is an open set, therefore f inverse of J is open set. Okay, we know any open set is measurable. Okay, this is actually in the Borel sigma algebra of R, and which is contained in Lebesgue measures. Therefore, any continuous function f from R to R is a measurable function. As a function from R with the Borel set of R to R, also f as a function from R. Now the sigma algebra is different, measure Lebesgue measure set to R. Please don't get confused, please understand. Okay, okay, this is a P.R.P. And fourth example I want to look at is suppose f from R to R is monotone. Let us assume increasing as usual. Okay, without loss of generality, f is increasing. Assume f is increasing. Right? Now let J be an interval. Right? Then I want to say that f inverse j is an interval. Remember, I will recall the definition of interval because that's very crucial for what you want to say. So when do you say a subset A of R is an interval? Because usually in analysis and topology, one has to define, okay, interval very precisely. You know only the collection of all intervals. You know, if I give a set whether it's interval or not, but there is an intrinsic definition. And I say A is an interval here for every x, y in A, and if z is in R is such that x less than y less than z, x less than z less than y, or maybe y less than z less than x, okay, maybe something happened, okay, z also belong to, that is, if you give me 2 points, this is my set J, okay, give me 2 points x and y, or maybe it's y and x, then any point in between them z should also be there. That's an interval definition. Yeah, right. Now let's look at, so I want to claim f inverse j is an interval. Notice that by this definition, if A is a singleton, this is an interval, and A is empty set also, this is an interval. Okay, if you have gone through my real analysis videos or book, you will know this, or even in topology course, you must have learned this. Anyway, so I want to claim this. If this is an interval, naturally it is going to be in Borel set, and hence it's also in measurable set. You understand? So I want to say this is an interval. So what does it mean? So it means start with an x, y in J, okay, and suppose I have x z less than y, I want to know whether z is in f inverse j. This is a question. Do you understand this? Okay, make sure that you understand the problem. So when does z belong to f inverse of j? Notice that the only way to work with inverse images, go back to the definition that if only if fz belong to j, right? Since f is monotone, it's actually increasing, and x is less than y. What does that mean? F of x is less than f of z, and that's less than f of y. Maybe less than or equal to, okay, it doesn't matter. Okay, right? Now, what do I know about j? J is an interval. And fx, fy are there. And z is a point in between. That means fz belong to j. If fz belong to j, that means z belong to f inverse of j. Right? So what I have proved? Take any 2 points x and y in f inverse j. Suppose z is a point in between x and y, then z is also in f inverse j. That means f inverse j is an interval. Have I proved it? Yes. Okay. P.R.P. Okay. Fifth example is an extension of example 2. Example 3. Yeah, this is example 3, right? Yeah, integrated function, right? Suppose EI are all measurable sets, are all in Borel set, okay? X, B, and EIs are subsets of X, and they are actually in B, and CIs are some real constant. Let us define fx to be summation Ci and integrated function of EI. So notice that what does it mean? It is a good idea to have a picture, because this kind of thing we are going to use often in the course. So let us have some kind of an idea, picture, and understand it better. Okay. So this is something like my x. Okay. And these are all my EIs. Notice that my EIs may also overlap. I do not know. Okay. Right. So what does it mean? So if x belong to one EI, that means f of x must be in Ci, right? But notice that this may be my E1, this may be my E2, my x may be in both. Then in that case, fx is going to be C1 times IE, that is C1 times IE1 of x plus C2 times IE2 of x and plus C3 times IE of E3 of x and so on. Okay, assume that x belongs to only E1 intersection E2, then what happens is this will be 1, therefore C1, this will be 1, therefore C2, this will be 0, therefore it will be C1 plus C2. Do you understand that? Therefore, okay, what is going to be x? Fx, do you know how to write it? Fx is going to be summation Ci, where I is said that, okay, this index I is said that my x belong to Ei. Only those Ci's you understand. I just deliberately making it, okay, a non-trivial example which is not given usually in measure. When you talk about measurable function, try to understand. This means what? Look at only those indexes I said that x belong to Ei, then do that. That's exactly what we did. You understand that? So this function is measurable. Okay, one can prove it directly. Okay, it's not difficult. Okay, but later we will see sum of measurable functions is measurable, scalar multiple of measurable function is measurable, therefore this will be measurable. That will follow easily. But okay, if you want, just try to prove it for only two things. For example, okay, alpha times I of A plus beta times I of B. Okay, A and B are measurable. Okay, try to prove this rigorously. But I just wanted you to learn how to work with this class of functions, because these functions are going to be used often later. Okay, now let's come back. But most often in the measure theory, we have to deal with functions taking values in extended real numbers. Real number system. What does that mean? That means fx may be plus infinity, or there may be fy, so the fx may be minus infinity. So my function f will be from xb to r extended. This is r union plus or minus infinity. Okay. In that case, how do I define measurability? Okay, how to define measurability of such function? It's again easy. We say that, okay, this is our definition. Yeah, from xb to re is measurable if and only if for every open interval j of r, okay, f inverse of j and f inverse of plus infinity and f inverse of minus infinity, they are all measurable. Is the definition clear? Earlier, when it takes real value only, then we insisted only measurability of f inverse j, but it may take infinity. Okay. For example, just to have an idea about this, let us look at R with our Lebesgue measurable sigma algebra. Alright. And let us look at with the E, which is non-measurable set. Right? Let me define a function f from R to R, okay, by saying fx equal to 1 if x belongs to let me see. Yeah, if x is not in 0 1 equal to x, if x is in 0 1 minus e equal to infinity if x is in e. Remember, my E is a subset of 0, 1. The one which you constructed, non-measurable set, is a subset of 0, 1. So I have this. So outside this, it's 1. Here, these are the points which are in, okay, and there are the points which are outside Y. Okay. So the X is in 0, 1 minus E, and Y is in E. Okay, then I am defining, right? Is the function measurable? No, because f inverse of infinity is E. Therefore, it's okay. It's a non-measurable set. Therefore, f is not measurable. Or maybe I can even define, just for fun, just to define this to be plus infinity, right? Then, so this is f inverse of minus infinity. Then sorry, make it minus infinity, right? And what is f inverse of minus infinity? That is your 0, 1 minus E. This is also non-measurable. Okay, right. So you can see I gave a lot of easy examples so that you become confident about the concepts, how to deal with that. One of the things which I did, that's a very important thing, which is summation Ci integrated functions of EIs. If EIs are measurable, this is measurable. These are called simple function, which is something analogous to step functions in Riemann integral. Learn these things well, okay? Life will be simple. Now what I am going to do is the next thing. I am going to prove equivalent characterization of measurable functions. I will start with the standard definition and then prove the equivalence of that definition with my definition with which we started. Okay, let's get started. So what is the standard definition? Let f from xb to r is measurable if for every alpha in R, the set, this is a standard notation in measure theory. This is by definition set of all x in x such that fx is greater than alpha, right? Which is same as f inverse of alpha infinity, alpha infinity, right? The inverse image of the set. Okay, if only this set is measurable. Please understand this. This is the standard definition. Okay, right. So we will prove it as a theorem with the other equivalent conditions because they are all very important. So let x be a measurable space. Let f from x to Re be a function. Then the following are equivalent. Okay, what are they? One, my definition, f is measurable. This is according to our definition. Second, okay, for each real number alpha, okay, f greater than alpha. Notice that what is this set? Please get used to this notation. This is a short-term notation used in measure theory. Fx is greater than alpha. This is measurable. 3, for every alpha in R, f greater than or equal to alpha is measurable, and 4 for every beta in R, f less than beta is measurable, and 5 for every beta in R, f less than or equal to beta is measurable. Okay. So what does it mean? I have alpha. This should f inverse of this set must be measurable is the second condition. The third condition says you also include alpha, and fourth condition says I have beta everything here. This inverse image of this set should be measurable, and fifth condition says you can even include this point. Okay, these are all very easy. Okay, so let us try to prove. In all these things, the standard trick is if I want to show something is measurable, there are essentially two ways. Try to see whether the complement is measurable, or try to write this as a countable union of measurable sets. Okay, those who has watched my topology course also will know if I want to show U is open, the standard trick is write it as union of open sets. How do I achieve that? For each x in U, you find an open set B such that x belongs to B, B is contained in U. Okay, but then it's arbitrary union, but the trick is the same. Okay, idea is the same. Okay, so let us get started. Let us try to prove. Okay, so we want to prove 1 implies 2. What does 1 say? F is measurable. What do I want to say? I want to, sorry, no, F is measurable. So this is 1. To show this, what I would show is to show, let alpha in R be given, I have to show this is measurable. Right? Now the standard trick is, let us start with alpha, right? But then you can write this f greater than alpha as a countable union of open sets, f not open set, measurable sets f inverse of alpha n, where n is greater than a. Okay. So as n increases, this one, this is n greater than alpha. Okay. And by our definition, this is an open interval, therefore this is a measurable set, and this is a countable union, therefore this is measurable. Is the proof okay? Pause, review, proceed. Then next we want to show 2 implies 3. What is 2? We know the measurability of f greater than alpha. We want to prove measurability of f greater than or equal to alpha. Right? So how do I prove that? So this is greater than or equal to alpha, right? That means it has to be f greater than alpha minus 1 by n, and it should be intersection of all those things. Right? This is intersection of this is f greater than alpha, right? If x belongs to this, that means fx is greater than alpha minus 1 by n for all n, right? That means if for this is only x is greater than or equal to alpha, right? And what do I know about these things? I know each one of them is measurable, okay, and it belongs to B, and B is a sigma algebra, right? Therefore countable unions are there, therefore countable intersections are also there, therefore this, okay, this intersection is in B. That is, this is in B. F greater than or equal to alpha, sorry. Okay, is that clear? So pause, review, proceed. I think I have put this. Okay, now I want to say 3 implies 1. So what is the trick? Because you can see 4 and 5 are essentially complements of the earlier results. So that can be deduced, right? That is the reason. So it's enough if I show 1 implies 2, implies 3, implies 1. So these are equivalent. And 4 and 5 are complements of 2 and 3, right? By taking complement, the result will follow. Is that are you clear? So I only have to prove 3 implies 1. Let us go to that. So to show 3 implies 1, what do I know? I know that f greater than or equal to alpha is measurable for any alpha, right? Now I want to show what are the things I want to show. One, it implies 1. That means if j is any open interval, say j equal to ab, then f inverse of j is measurable. That is in B. And similarly, f inverse of plus infinity is in B, and f inverse of minus infinity is in B. These are the things I have to prove. Okay. Now let's look at f. Okay. What is f inverse of j? F inverse of j is a less than f less than b. Right? Set of all x so that fx is greater than a and fx is less than b. So this is therefore intersection of f greater than a and intersection of f less than b. Okay. Notice that f less than b is f greater than or equal to b complement. This is equal to, right? And what we know, this is in b. Since b is a sigma algebra, its complement, this is also in b. Is that okay? Right. So this is in b is still clear. Now why is this in b? Now this again f greater than a is equal to union of f greater than a plus 1 by n, greater than or equal to 1 by n for all n. Yeah, by Archimedes property, if fx is greater than a, therefore fx minus a must be greater than or equal to 1 by n for some n. By Archimedes property, that is n into fx minus a must be greater than or equal to 1. That's all you are using. Okay, this is Archimedes property. Okay, and by 3, these are all measurable, and this is a countable union, right? Therefore f of a is a countable union of countable family of measurable sets. Therefore measurable. Okay, so what have you shown now? So I have shown that f inverse of j is measurable. This is shown. Next I would show this, but that's very easy, because what is f inverse of infinity? This is intersection of f greater than or equal to n for all n, right? By assumption, this is each one of them is measurable, and this is in B. B is a sigma algebra, therefore countable union, countable intersections are also there. Therefore this is there. For f inverse of minus infinity, then I will say f is less than or equal to minus n, or simply say less than minus n. F less than minus n is a complement of f greater than or equal to minus n complement, and this is measurable. Therefore this is measurable because of B is sigma algebra, and countable intersection of sets in B, and B is a sigma algebra, therefore this is also in B, therefore this is also in B. So we have shown that 3 implies 1. Okay. So, and the rest 4 and 5 are easy. So do it as an exercise. Okay. You simply say how to take complement and prove that. Okay. So the most popular definition of measurability is f greater than alpha definition. For each alpha in R, f alpha is in B, is a measurable set. Okay. So I do not distinguish between plus infinity, minus infinity, etc. Everything is taken care by this definition as we saw. Okay. So pause, review, proceed. next thing we want to talk about algebra of measurable functions. Let me see whether I started the thing. Yeah, sure. See how much paranoid I have become. Okay. It has to be done with a little care because of we are allowing extended real number values. Okay. We will come to that first. But the most important thing I want to do is the following. We saw f is measurable implies for each alpha real, f greater than alpha is measurable, right? We want to first generalize this object. That's the first important observation. If f and g are measurable, right, f greater than g is measurable. This is set of all x so that fx greater than gx. This is a very, very basic result. Okay. So if g is a constant, we have proved it. If g is a constant alpha, that's what the definition of measurability. Yeah. So therefore, what do I have to do? Remember what I said? I said that to prove measurability of a set, the standard trick is either to prove its complement is measurable. In this case, f less than or equal to g. That doesn't seem to be any easier. But the other one is write it as a countable union of measurable sets. Yeah. So let us try to do that. How do I get it? Now let us see. My fx is here and gx is here, right? But remember, if fx, okay, sorry, gx is greater than fx, sorry. Okay, fx is f is greater than g, right? So I would write it carefully. Yep. Now there is always exists a rational number in between, right? Density of rational. So that is the basic idea. Therefore, f greater than g, I can write like this, is union of r in q, so that f greater than r greater than g. But this is union of r in q and f greater than r and intersection with f greater than r, yeah, and g less than r. Okay. Now by measurability thing, 1, 2, 3, 4, 5, we know this is a measurable set. This is also a measurable set, right? This will be countable union. Notice that some of them may be empty. For example, this may be non-empty, this may be a non-empty, but their intersection may be empty. But in any case, each one of them is measurable, and I am taking countable union of measurable sets, therefore it is measurable. Do you understand that? I have to allow any R, okay? But the same R appears both the things. This is written as this. Okay. Now start with any x. What does it mean? Okay, I have to say x belong to this. Does x belong to that? Because let's look at, therefore, fx is greater than gx. Right? By density of rational, there is an R, a rational number strictly in between gx and fx. Right? Therefore, my f is greater than r. Yes. Therefore, this x with this property belong to that particular r. F greater than r, g greater than r. Okay, for this set. Are you following? Yeah. If x belong to this, then x belong to this. Which are any r, so that r is rational and it lies strictly between gx and fx. Okay. Pause. Review. Proceed. Okay, I seem to be running out of pages, so maybe it's a time for me to wind up. But let's do one more thing. If f is measurable, again f from x, a measurable space to extended real numbers, okay? And c is a real number, then f plus c is measurable. This is easy, right? F plus c greater than alpha is same as f greater than alpha minus c, right? That's what's measurability. This is clear. The third thing, if c is a constant and c times f is measurable, right? If c is 0, then c times f is 0, Any constant function is measurable, therefore it's okay. If C is positive, CF greater than alpha is same as F greater than alpha by C. If C is positive. If C is negative, CF greater than alpha is same as F less than alpha minus C. Right? So each one of them is measurable. Okay? Right. Now let us see if F and G are measurable. Let me assume F and G to start with are real valued functions. Okay, not extended real value. Then I want to show F plus G is measurable. Okay, so what is that I have to do? I have to prove F plus G, give me any alpha in R, I have to show this is measurable. That is whether it's in B. But this object is nothing other than F greater than alpha minus G. Now notice that G is measurable, C equal to minus 1, therefore C times G is minus G is measurable, right? And by 1, therefore C F greater than alpha minus G is measurable because of this 2, right? Here I used 3 and here I used 2. This is measurable, and by 1 F greater than alpha minus G is measurable. This is by 1. Yeah. So we have proved F plus G is measurable. Here. Hi, I had to break with our final conclusions. We will do it, then we will end the session. So the proof, if F and G from XB to extended real number system measurable, okay, then F plus G should make sense. That is, F plus G at X should be Fx plus Gx. So that means it should not be of the form infinity plus minus infinity or minus infinity plus infinity. Okay, so we assume that for all x in capital X, F plus G at X makes sense. Okay, in that case, the earlier proof, that is F plus G greater than C equal to F greater than C minus G makes sense. Okay, yes, makes sense and measurable. Okay, right. And the next one is about product. Before proving product, what we will do is we will make an observation, call it a lemma. If F from XB to R, let us assume only R, measurable, and from R to R, G is continuous. That is, I have X to R, F, this is measurable, and this R to R, G, continuous. Okay, then I have a map G composite F from XB to R. We want to say this is measurable. The proof is easy. Let us start. Yeah, right. Okay. The proof is easy because let us look at any kind of set J, which is an open interval in R, or even alpha infinity, G composite F greater than alpha. This is set of all x in X such that G of Fx is greater than alpha. But this is same as set of all x in X such that Fx is, okay, G composite Fx is greater than alpha. That means I am looking at F, let me rewrite. This simply means G of Fx is greater than alpha. That means you are looking at G inverse of this fellow, alpha to infinity. Right? This is same as saying this is, you are looking at G composite F inverse of alpha to infinity, but this is F inverse of G inverse of alpha to infinity. Right? but G is continuous. Alpha to infinity is an open set. If you want, make it interval also. Okay, instead of alpha, look at G comma F. Okay, inverse of J. Okay, therefore this is F inverse of G inverse of J. Now G is continuous, therefore this is an open set. This is an open interval, and continuous image of an open set must be open, therefore this is our open set. And since F is measurable, okay, and G inverse J is where it's an open set, where in R. So again we know that this is union of some ik countable number of open intervals. It's actually disjoint, that doesn't matter, right? Therefore F inverse of G inverse of J is F inverse of union ik, k. Okay, and since F is measurable, each of them is measurable. This is a countable union, therefore this whole thing is measurable. Notice that we made use of a general result. If F is a function from a set x to y, just a set. These are all sets. This is just a function. And if bi is are subsets of y, then F inverse of union bi is union I F inverse of bi. These are all standard result, usually done in foundations. Okay, that fact we used. Therefore G inverse of J is a countable union of intervals ik. Therefore F inverse of open intervals ik will be measurable. Therefore this whole thing is a countable union, therefore it is measurable. So what you have shown is, if F is measurable from x to R and G is continuous from R to R, then G composite F from x to R is measurable. Okay, now we want to make use of this. This is a very powerful result. Okay, for example, let us look at F measurable, x to R measurable. So this is pause, review, proceed. Okay, now R to R, let us look at the function G x. Okay, let us call it y going to y squared. Okay, this is a continuous function. Therefore, what is G composite f of x? That is G of f of x, but that is fx whole squared. That is same as what we call f of f squared of x, right? Therefore, G composite f is nothing other than f squared, right? Since f is measurable, then f squared is measurable. That's a conclusion. And similarly, we will do a lot of other things. Suppose f from x to R is measurable, and R to R is a mod function, that is y going to mod y, then this is continuous. Therefore, we conclude G composite f in this case will be mod f, because G composite f of x will be G of f of x, which will be mod fx, but that's the definition of mod f at x, right? Therefore, mod f is continuous. Okay. Similarly, if f and g are measurable, these are the applications. Okay. So these are the applications of this theorem. This is a lemma. Its applications are what we are looking at. First application. This is the second application. Okay. And third application is f and g x to r are measurable. And remember, we define maximum of g at x by definition is maximum of these two real numbers fx and gx. Okay, right? Now the function, this is measurable because maximum of f and g, remember maximum of a and b is we have done that. Okay, that will be mod a minus b plus, see, this is a and b may be somewhere, I do not know. The midpoint is a plus b by 2. So if I want the maximum, what I should do, I have to go a plus b plus, the distance is mod b minus a or mod a minus b by 2. So I add them, right? Therefore maximum of a and b, these are all done in real analysis by me. In my book also we can see that. Therefore by definition this is a plus b plus mod a minus b by 2, right? Therefore maximum of f and g will be f plus g plus mod f minus g by 2. Now this is this we know is measurable, and for f minus g is measurable, modulus of that is measurable, sum of two measurable functions is measurable, scalar multiples of a function, measurable function is measurable, therefore this is measurable. Similarly minimum of f and g, from here I have to go backward. That means this will be, minimum will be a plus b minus a minus b mod by 2, right? So this will also be measurable. So these are the applications. And more generally something like, if f is measurable, and look at exponential function from r to r, that is y going to e power y, then e power f will be measurable. And also you look at r to r, suppose alpha is positive, then taking x to x power alpha, okay, these are all continuous function. Therefore if f is measurable, f power alpha will also be measurable. Okay, now come back to f times g. Notice that 4ab is a plus b whole squared minus a plus b whole squared minus a minus b whole squared, right? Therefore ab equal to this by 4. Therefore fg equal to 1 by 4 of a plus g whole squared plus f minus g whole squared. Now if f and g are measurable, then f plus g is measurable, and hence f plus g whole squared is measurable. Similarly f minus g whole squared is measurable, and hence sum of these functions is measurable, scalar multiple, therefore fg is measurable. Right? The last thing we want to do is, again, suppose f is measurable function, okay, assume fx is not 0 for any x, okay, then I can define 1 by f, that will be a function from x to r. I want to claim 1 by f is measurable. The proof is again the same way. Let us look at this g, which is from r star to r star, that is non-zero reals, y going to 1 by y, these are all non-zero. This is a continuous function, right? Therefore f actually takes values from x to r star to r star, this is contained in r, that's okay, and y going to 1 by y, this is continuous. Therefore g composite f of x will be g of f of x, that will be 1 by f of x, that is 1 by f at x. Okay, hence 1 by f is also measurable, and similarly if f is measurable and g of x is different from 0, f by g is measurable because it is f times 1 by g. This is measurable, this is measurable, product is measurable. Okay, so pause, review, proceed. Yeah, I know I went a bit fast. Okay, that's because since I stopped it, it has been really bothering me to finish it. Okay, but I hope I explained everything. Please go through it. Okay, in case of difficulty, you please write a comment in one of the next few sessions. I will take it up again if there is difficulty. Hopefully there should not be. These are all easy. You must have done similar things in continuous functions, algebra continuous function, algebra differential function, the same kind of logic. Okay, right. Stay safe. We'll meet again.